In this recording, I'm going to work through the solutions on this worksheet, which is on confidence intervals for one population mean when sigma is known. Now, sigma represents the population standard deviation. So this worksheet has questions pertaining to the case when the population standard deviation is either given to us or we know the population standard deviation through some means. The first set of questions is a simple one, just to find the confidence interval and the related confidence level, the alpha and the alpha by 2 values. That's going to be the first step in the process to create a confidence interval. So this step is very important. The first question is not asking us to find the exact confidence interval. It's only giving us some practice on how to come up with an alpha value and an alpha by 2 value when only the confidence interval percentage is given to us. All right. So they've given us an 85% confidence interval, and we have to find CI, which represents confidence interval. CL stands for confidence level, and then alpha and alpha by 2. So very quickly here with a diagram, let me explain these terms. Then it'll be easy for you to come up with these values. All right. Now, confidence interval represents how wide our interval is going to be. So if we have a standard normal curve, all right, if we have a standard normal curve, a confidence interval is going to be around a sample mean value, correct? It's going to be about a sample mean value. We are going to come up with an interval, and this percentage, the confidence interval percentage, tells us how wide across this horizontal line with the sample mean at the center is the interval going to be. All right. So an 85% confidence interval. Now, confidence interval can be written as a percentage. So for the first one, 85%, I'm just going to write 85% for the confidence interval. Now, the next information they want is the confidence level. What is confidence level? Confidence level is the confidence interval transformed to a decimal value. All right. So the decimal equivalent of 85% is 0.85, correct? 85 divided by 100 is 0.85. So confidence level is going to be 0.85. And in this diagram, the confidence level is this area bounded by the end points of our interval that we are going to find. All right, so the end points of the interval are, let's say, over here on the horizontal line below the curve, correct? And the area bounded by the end points represents this 0.85. Okay, it's the region bounded by the end points of the confidence interval. 0.85 also refers to the probability that the population mean is going to be contained within this interval. So 0.85 is not only the area bounded by the endpoints of the interval, but it also represents the probability that the population mean is going to fall within this interval. All right. What is alpha? Alpha is the unbounded area outside the interval. So that means alpha is this area plus this area. There are unbounded areas on both sides of the curve, correct? And these unbounded areas represents alpha. How do we find alpha? It's 1 minus whatever the bounded area is. So if the bounded area is 0.85, then all you do is to find alpha is 1 minus 0.85, which is going to be equal to 0.15. All right? So that's these two areas together. So I'm going to write the value of alpha as 1 minus CL. That would be the formula to use because the total area under the curve is 1 and the bounded area is 0.85. Therefore, the unbounded area on each side is going to be 1 minus 0.85, which gives us 0.15. All right, 0.15. Now, what is alpha by 2? Alpha by 2 is the area of each side, the unbounded area on each side. All right, now this is not a perfect diagram, perfectly scaled diagram, and it appears that on one side the area is a little bit larger than what we have on the left-hand side, but it should be the same. All right, I'm sorry that it's not a properly scaled picture, but just know that both sides must have the same area. And because of that, all we do to find alpha by 2 is take your alpha and divide it by 2. So it's going to be 0.15 divided by 2, which is going to be equal to 0.075. Right? Part B says is a 95% confidence interval, and we have to find first the same data points, the confidence interval, what's the confidence level associated with the interval, alpha and alpha by 2. So if it is a 95% confidence interval, we can just write 95% for the CI. For CL, it's going to be the 95% converted to its decimal equivalent. Again, just divide it by 100 and you'll get 0.95. Alpha is 1 minus 0.95. So 1 minus whatever the confidence level is. So it should give you a value of 0.05. Alpha by 2 is 0.05 divided by 2. Therefore, it's 0.025. All right. And finally, we have a 99% confidence interval. So we just write 99% for the CI. CL would be, again, 99% converted to decimal, so 0.99. Alpha is 1 minus 0.99, which is 0.01. And finally, alpha by 2 is 0.01 divided by 2, therefore 0.005. All right, so that completes question number 1. Now, question number 2 is checking our understanding of the assumptions that need to be satisfied in order to be able to use the Z-interval procedure. So it says, in each part, assume that the population standard deviation is known. Decide whether use of the Z-interval procedure to obtain a confidence interval for the population mean is reasonable. Explain your answers. So the first question says the simple random sample data contain no outliers. The variable under consideration is roughly normally distributed and the sample size is 20. Given these conditions, can we use the Z-interval procedure or not? Now, before that, I'm going to just list the assumptions that are required in order to use the Z-interval procedure. So let me write that here. Get my pen out. The assumptions. assumptions that we learned was that, first of all, the sample must be a simple random sample, and that will hold true for any statistical study. All right, any statistical procedure that you will use to perform a statistical inferential study must satisfy this condition that the sample must be obtained from a simple random sample. Number 2 says the variable must be normally distributed or come from a large sample. All right, or must be a large sample. And number 3 says the sigma, that is the population standard deviation, must be known. So let's see whether the conditions given here in part A satisfy these assumptions. Now, question number 2 is checking our understanding of the assumptions that must be satisfied in order to use the z-interval procedure to find a confidence interval. It says here, in each part, assume that the population standard deviation is known. Decide whether use of the z-interval procedure to obtain a confidence interval for the population mean is reasonable. Explain your answers. Part A gives us some conditions. The simple random sample data contains no outliers. The variable under consideration is roughly normally distributed and the sample size is 20. Now, before we proceed with this, let me list on the side the assumptions we had learned that must be satisfied in order to use the z-interval procedure. So let me get my pen out here. So the assumptions for a z-interval procedure, number 1 is that the data must come from a simple random sample. All right, the data must be obtained using a simple random sample. Number 2 says the variable must be normally distributed. So it should be a normally distributed variable, or it must be from a large sample. All right, or a large sample must be used. And number 3 says the population standard deviation must be known. If all these conditions are satisfied, we can go ahead and apply the z-interval procedure. So let's see what conditions are given in part A. It says the simple random sample data contain no outliers. So no outliers, but before that they say it's the simple random sample data. That means the first condition is satisfied. It's as the data was obtained from a simple random sample. And then it says the variable under consideration is roughly normally distributed. So that means the second assumption is also satisfied, because they've told us that the data, that the variable that we are studying, or that is being studied, is roughly normally distributed. So this was good. And they've already told us earlier that the population standard deviation is known, sigma is known. So the way you're going to answer this question, explaining or justifying your answer, is yes, the z-interval procedure, sorry, let me just bear with me. The z-interval procedure can be used hold on one second, because it is given that we have to mention that these three conditions are fulfilled, because it is given that the data is obtained from a simple random sample, that it is roughly normally distributed, and population standard deviation is known. So basically, they've told us that all these all these conditions are met. All right, so we have to just read the given conditions and check it against the assumptions and make sure they are met and put it in our answer. All right. Let's look at the conditions given in part B. It says the distribution of the variable under consideration is highly skewed and the sample size is 20. All right. Now, previously they had told us that the data was obtained from a simple random sample. That is not mentioned in part B. All right. So the first condition is unknown. All right, we don't know whether. So for the second one, it doesn't tell us whether it's an SRS that was used to obtain the data. So that condition is not satisfied. Let's see what other conditions are satisfied or not satisfied. Okay, it says the distribution of the variable under consideration is highly skewed. So when it is a highly skewed distribution, that means it's not normally distributed. It's a highly skewed distribution of the variable that's being studied. However, even if it is not normally distributed, if a large sample size was used, right? If a large sample size was used, then we can assume, based on the central limit theorem, we can still assume that it's going to be a normal distribution. Okay? Look at the sample size given. Here it says the sample size is 20. What is the criteria for a sample size to be considered large? So let me write that here. All right. A small sample size, small n represents sample size, is a size less than 15. All right. A medium sample size is anywhere between 15 and 30. If the sample size is a value between 15 and 30, all right, it's considered a medium, moderately sized sample. And a large sample size would be a size greater than 30. All right. Here it says the sample size, actually let's just make it greater or equal to 30. It says here the sample size is 20, so it falls under the medium category. But because it says it's highly skewed, the variable is highly skewed, and also they haven't told us whether it's obtained, if the data was obtained from a simple random sample, we cannot use the Z interval procedure, right? So your answer should be phrased like this: no, do not use the Z interval procedure as it is not known, all right? So we do not know whether if the data is from a simple random sample, the variable is not normally distributed, correct? It tells us, it's given to us that it's highly skewed, so the variable is not normally distributed. And also the sample size n equals 20 is not large enough to assume a normal distribution. All right, that's good enough explanation. Now let's look at part C, which says the simple random sample data contain no outliers, the sample size is 250, and the variable under consideration is far from being normally distributed. So far from being normally distributed would mean that it is not normally distributed, correct? So let's write that it's not normally distributed. However, it says before, no, there are no outliers and the sample size is 250. So when you see that the data is not, the variable is not normally distributed, check for the sample size. If the sample size is large enough, that is greater than 30, then you can assume that it's going to be normally distributed. All right, so here the sample size is 250, right? So that would mean that you can assume that it's going to be normally distributed. Additionally, it says no outliers, which is also a good news. All right, so it does satisfy our conditions, the assumptions. It is SRS. It says here it's simple random sample data. It says normal distribution or large sample. So even though it is not normally distributed, but because the sample size is large enough, we can assume this assumption is satisfied, and well, sigma is known was said earlier, right? It said earlier that the population standard deviation is known. So all the conditions are met. We can say here, yes, we can apply the Z procedure, Z interval procedure, because even though it's not the variable, is not normally distributed, distributed, the sample size of 250, the sample size of 250 is large enough. To assume it will be normally distributed. It will be normally distributed, and additionally you can say that there are no outliers, and it's also given that it's a simple random sample, and of course the population standard deviation is known, right? Now for question number 3, we are being asked to find a confidence interval from the data provided to us in this question, all right? So it says here, in each of the cases below, use the Z interval procedure to find a confidence interval for the mean of the population from which the sample was drawn. So let's look at the data that's been given to us. Now this is a problem which is not application based. It's a straightforward problem. They've told us which procedure to use, the z-interval procedure, and they've also given us specifically the data points that we will need to find the confidence interval. All right. If this were an application word problem, then we would have to carefully read the problem and first of all determine whether which procedure we could use. It could be the z-interval or the t-interval, depending on whether they've provided us the population standard deviation or not. And also we would have to extract the data from the wording of the problem. All right, but luckily for this one, we are already provided with the data. So let's go through the data. X bar is the sample mean, correct? So let me write that down here. X bar is sample mean, and we build the confidence interval around the sample mean. So it's important to have a value for the sample mean. N represents the sample size. That also figures in the equation, in the formula for the confidence interval. So we need this data. And then sigma. Sigma is the population standard deviation, correct? So it's important that the population standard deviation is provided to us, because not only it figures in the formula, but if we have to use the z-interval procedure like the question asks us to, then the population standard deviation better be given to us. All right. And then the confidence interval, okay, that's the width of the interval, is given to us at 95%. So let's try to go through the steps using the data given to us. So first, it asks us to find list what the confidence interval is. Then CL represents the confidence level, and from there we will get the alpha and then the alpha by 2 values. All right. So confidence interval is 95%, therefore CI will also be 95%. Confidence interval is written in percentage form. CL is confidence level, which is the confidence interval converted to decimal. So just divide 95 by 100 and you'll get 0.95, which is the decimal form of the percentage. Alpha is 1 minus the confidence level. So our confidence level is 0.95. Therefore, 1 minus 0.95 is 0.05. That's alpha. And then alpha by 2, we have to divide alpha into 2 equal parts. So it's going to be 0.05 divided by 2, which is 0.025. All right. Now, in the next step, it says write the formula for confidence interval. So the formula is going to be X bar plus minus, and then we have to add a quantity to the sample mean to find the endpoints of our interval, and that will come from z of alpha by 2 multiplied by sigma over square root over n. All right. So this z of alpha by 2 times sigma over square root over n represents the margin of error. The margin of error. Okay, and then it says include a clearly labeled diagram showing the confidence interval and alpha. So let's draw our diagram here. So it's going to be a normal curve. Okay, so here's my picture of the normal curve. At the center of point, there's going to be this X bar value, because we are going to build our interval around the sample mean, also called the point estimate. So this is going to be the center point, and around the center point will be the 2 endpoints of our interval. Right? It's going to be, let me just move this a little bit to the right. Okay, let's say it's here. All right. So these are going to be the endpoints of the interval. Now what I'm going to do is I'm going to extend the endpoints up to touch the curve. All right. So I'm going to, let me just draw a slightly symmetrical figure. I'm going to extend this a little more to the, just give me a little bit of time here. All right, move it further out. Okay, so the lower end of the interval is going to be to the left hand side, and the upper end is going to be to the right hand side. And this area bounded by the endpoints of the interval will be 0.95. All right. It also tells us that the probability that the population mean will lie within the interval is 0.95. That's another way to interpret the confidence level. All right. And then we have two ends of the curve which are unbounded, this white area which is outside the interval, and that area is what alpha is. All right, so here alpha, the two unbounded areas on each side, on either side of the curve, represents alpha. So alpha is 1 minus 0.95, right? 0.05. How do I get it? 1 minus 0.95. The same thing that we did here to find alpha. Okay, and then we also have to note the area on each side of the interval, on each end of the interval rather. Okay, just excuse this figure because this doesn't look to scale, but the two ends must have equal areas. All right, so how do we get the values of each end? You take your 0.05 divided by 2, and 0.025 is the area on each side. 0.025 on the right hand side and 0.025 on the left hand side, and it's alpha by 2. So this is a clearly labeled diagram now that we have. Okay, and these are going to be the end points. All right, so I'm going to mark the end points of the interval as minus z of alpha by 2, and this endpoint here, and then another endpoint as positive z of alpha by 2. These are going to be the two endpoints. So now that we have a figure with us, all right, next step in the question says find z of alpha by 2. All right, so we have to find the z value whose area to the left is 0.025, and likewise whose area to the right is 0.025. Okay, so we will get two z values. One of them will be a negative value. The one on the right hand side will be a positive z value. Now, in order to find the z value, you need to refer to the table, or if you have a graphing calculator, you can use that to find the z value. But let me just use the table. Now, let me pull that up just a second. Here's our table. All right, now in this table here, there is a special table just for specific alpha values, 0.10, 0.05, 0.025, 0.01, and z of 0.005. These are the special alpha values that we use in order to find confidence intervals and also for hypothesis testing, all right, for critical values, which we'll discuss later on. And this table is found, okay, just below the table 4, which is the T table. Okay, just below the table, there is the concise truncated Z table for special alpha values. Now, you can also find the same Z values from this table here, which is table 2, but this a lot of values in this table, so it may be hard to find the values. It may be more time consuming. So just refer to this truncated table. The whole idea of giving this table is for you to find the values easily. All right. So over here, we have z of 0.025 as 1.960, right? So it's 1.960. So I'm going to go back to my worksheet here. So z of alpha by 2 is 1.960 on the right-hand side. On the left-hand side, it's negative 1.960. So z of alpha by 2 is 1.960. All right, that's what z of alpha is from the table. All right, so we have now we have to find the confidence interval now. Let's just apply the formula. So again, I'm going to just rewrite the formula here. It's always have the formula in front of you. That way you don't make mistakes plugging in the values. So z of alpha by 2 times sigma over square root over n, correct? So x bar was given to us as 25. So let's write that down. Okay, what happened to the formula? 0 of alpha by 2 times sigma divided by square root over n. Okay, so x bar was 25. Let's write that. Then plus minus, that's a part of the formula. And then z of alpha by 2 we just found is 1.960. So I'm going to write 1.960. Now, common mistakes once in a while it happens is to, instead of writing 1.960, students write 0.025, just alpha by 2. All right, it's not alpha by 2 that you are multiplying with. It is z of alpha by 2. In other words, you have to find the z value corresponding to alpha by 2, correct? So 1.960 is what we found from the table. It's a z value, not area. It's the z value. Times sigma, population standard deviation, is given to us as 3. Okay, so 3 divided by, and n was 36. So divided by square root over 36. 3 divided by square root over 36. So let's continue. We have 25 plus minus 1.960 times 3 divided by square root over 36 is 6. So we have 3 divided, this is multiplication, all right? So 3 divided by 6, which is 1/2. So we will have 25 plus minus. So 1.960 times 1/2. All right, 1/2 is 0.98. And then when we add and subtract 0.98 from 25, we get an interval of 24.02 to 25.98. All right, so this is our confidence interval, a 95% confidence interval. Okay, so we found the endpoints of our confidence interval. Always make sure you write the lower end of the value first, lower end of the interval first, and then to upper end. All right, so lower to upper. Now, interpretation is very important for confidence intervals and later on for hypothesis testing. It's important that you interpret, or rather write the interpretation in correct order form. All right, there are some phrases that need to be included in the interpretation. You're going to start by saying, we are 95% confident, or we can be 95% confident because the interval that we just found was based on the confidence interval that we were asked to find. All right. If this were a different percentage, if it was a 90% confidence interval or a 99% confidence interval, these values would have been different. The endpoints of the interval would have been different. Therefore, it's very important to qualify it. So we are 95% confident that the population mean will be contained within the interval 24.02 to 25.98. So it's very important that you include these phrases. We are 95% confident. Then the next phrase is the population mean will be contained. All right. It's not the sample mean. Make sure you mention the population mean will be contained. We are drawing inferences on the population mean, not the sample mean is an accurate, is a precise value. It does not need to be contained in within an interval. It's the population mean which is not known to us, and we are trying to estimate the population mean. We are trying to draw an inference on the population mean based on our precise sample mean that we found from our data. And then, of course, within the interval, write the endpoints of the interval. Now, each of these phrases have points assigned to it. All right. So if you miss any of these, keep in mind you will lose the points for any of the missing phrases. It's very important to write what confidence interval you use. So we are 95% confident, and then what you are drawing the inference on, the population mean will be contained, and then of course the endpoints of the interval, right? Now this is part B of question number 3, which is also about finding the confidence interval, but they have given us a different percentage to use to find the confidence interval, and some of these values, data points given to us are also different. Now, I went through a rather detailed explanation in the previous question of how to find the confidence interval. So I'll try to speed up through this one. If you need additional explanation, please look up the video of the previous problem. All right, you may want to rewind and look that up again to understand why we are doing certain things. But I'll also keep explaining, but it won't be as detailed. All right. So over here, it says, what is the confidence interval, CI? So that's 90%. Let's write that down. Okay, so CI is going to be 90%. CL is the confidence level, which is derived from the percentage value. So just find the decimal of 90%, which is going to be 0.90, right? And then alpha is the area, is the unbounded area outside of the confidence level, right? So alpha is 1 minus CL. So that's 1 minus 0.90, which is 0.10. And alpha by 2, just divide alpha by 2. In this case, 0.10. Right? It's 0.10 divided by 2. So it's 0.05. That's the area on both ends of the curve. All right. The formula for confidence interval, the same that we used in the previous problem. It's going to be the X bar, the sample mean, and to it we add and subtract the margin of error, which is given by the formula Z of alpha by 2 times sigma divided by square root over n. All right, so this sigma is the population standard deviation. And since we know the population standard deviation, we are going to use the Z interval procedure to find our confidence interval. Then it says show all calculations, which we will, but first we have to include a clearly labeled diagram showing the interval and alpha. So let's do that. I'm going to sketch here. the standard normal curves to start with. And then at the center, we have our x bar around which we are going to build our confidence interval. So the endpoints of the interval, let's mark them here. Okay, so these are going to be, let's say, the endpoints of the interval. We don't know the actual values yet. That's what we have to find. But we've marked the endpoints, all right? And then we extend these endpoints up through the curve. And this area, this bounded area within the endpoints of the interval is our confidence level value, which is 0.90. All right. In other words, this also represents, this 0.9 also represents the probability that we can find the population mean within the interval that we are going to come up with. All right. Now then we have two outside areas, unbounded areas, which represents our alpha. Okay, that's alpha, which is 0.10. How did we get that? By doing 1 minus 0.9, right? 1 minus CL. So alpha is this the total unbounded area on both sides. That's alpha. But we need to know the area on each side, and that's alpha by 2. Okay, that's alpha by 2. It will be equal on both sides because this is a symmetric curve. So 0.05 is alpha by 2, and then the area on the right hand side, right end, is also 0.05. And now we have to find z of alpha by 2. All right, z of alpha by 2 on the right hand side, and also the z value on the left hand side, which will be negative z of alpha by 2. On the left hand side, z will always be negative. On the right hand side of the center point, z values will all be positive. Remember that. All right. So on the left hand side, it'll be negative z of alpha by 2. On the right hand side, it'll be the same value, but it'll be a positive value. All right. So when we say negative z of alpha by 2, it says find z of alpha by 2. We know alpha by 2 is 0.05. So that means we are looking for z of 0.05. We have to go to our table. Let's do that. Again, use the special table here. And it's z of 0.05 this time. All right, it's z of 0.05. So the z value, whose area to the right is 0.05, is 1.645. So we have to take that value and put it here. Just a second. So z of 0.05 is 1.645, right? That's the z of 0.05. So let's find the confidence interval now. Again, have the formula in front of you one more time. So x bar plus minus z of let's write it as alpha by 2, and then times sigma over square root over n. Correct? So x bar given to us was 35. That's the sample mean. So it's 35 plus minus z of alpha by 2 we just found from our table is 1.645, and then sigma given to us is 4. So let's write the 4, and divided by square root over n was 25. So I'm going to write square root over 25. Right? So we'll end up with 35 plus minus 1.645 times 4 square root over 25 is a 5. So again, this is a multiplication. 1.645 times 4 divided by square root over 25. And when we do this calculation, you have to do the 1.645 times 4/5 first, and then add that number, that value, to add or subtract that value to the 35. So 1.645 times 4/5 is 0.8 gives us 1.8. 1.316. All right, so now we first subtract and then we add. So 35 minus 1.316 is going to be 33.68, and 35 plus 1.316 is going to be 35.316. All right, so these are the endpoints of our confidence interval. And then finally, we have to write the interpretation in the expected form. So that we're going to write it as we are 95%, sorry, this is a 90% confidence interval, isn't it? Yeah, it's 90% confidence interval. So make sure you write that correctly. We are 90% confident that the population mean will be contained within the interval, of 33.68 to 35.316, right? Now, before moving on to the next problem, I just want to make a correction to a calculation error I have here. 35 plus 1.316 should be 36.316. So I apologize for that. It should be a 36.316, right? 35 plus 1 is 36, and same thing here. We need to correct that. It's 36.316. So it extends, the interval extends from 33.68 on the lower end to 36.316. Now this is part B of question number 3, which is also about finding the confidence interval, but they have given us a different percentage to use to find the confidence interval, and some of these values, data points given to us are also different. Now, I went through a rather detailed explanation in the previous question of how to find the confidence interval. So I'll try to speed up through this one. If you need additional explanation, please look up the video of the previous problem. All right, you may want to rewind and look that up again to understand why we are doing certain things. But I'll also keep explaining, but it won't be as detailed. All right. So over here, it says, what is the confidence interval, CI? So that's 90%. Let's write that down. Okay, so CI is going to be 90%. CL is the confidence level, which is derived from the percentage value. So just find the decimal of 90%, which is going to be 0.90, right? And then alpha is the area, is the unbounded area outside of the confidence level, right? So alpha is 1 minus CL. So that's 1 minus 0.90, which is 0.10. And alpha by 2, just divide alpha by 2. In this case, 0.10. Right? It's 0.10 divided by 2. So it's 0.05. That's the area on both ends of the curve. All right. The formula for confidence interval, the same that we used in the previous problem. It's going to be the x bar, the sample mean, and to it we add and subtract the margin of error, which is given by the formula z of alpha by 2 times sigma divided by square root over n. All right, so this sigma is the population standard deviation. And since we know the population standard deviation, we are going to use the z-interval procedure to find our confidence interval. Then it says show all calculations, which we will, but first we have to include a clearly labeled diagram showing the interval and alpha. So let's do that. I'm going to sketch here the standard normal curves to start with. And then at the center, we have our x bar around which we are going to build our confidence interval. So the endpoints of the interval, let's mark them here. Okay, so these are going to be, let's say, the endpoints of the interval. We don't know the actual values yet. That's what we have to find. But we've marked the endpoints, all right? And then we extend these endpoints up through the curve. And this area, this bounded area within the endpoints of the interval is our confidence level value, which is 0.90, all right? In other words, this also represents, this 0.9 also represents the probability that we can find the population mean within the interval that we are going to come up with, all right? Now then we have two outside areas, unbounded areas, which represents our alpha. Okay, that's alpha, which is 0.10. How did we get that? By doing 1 minus 0.9, right? 1 minus CL. So alpha is this the total unbounded area on both sides. That's alpha. But we need to know the area on each side, and that's alpha by 2. Okay, that's alpha by 2. It will be equal on both sides because this is a symmetric curve. So 0.05 is alpha by 2, and then the area on the right hand side, right end, is also 0.05. And now we have to find z of alpha by 2. All right, z of alpha by 2 on the right hand side, and also the z value on the left hand side, which will be negative z of alpha by 2. On the left hand side, z will always be negative. On the right hand side of the center point, z values will all be positive. Remember that, all right? So on the left hand side, it'll be negative z of alpha by 2. On the right hand side, it'll be the same value, but it'll be a positive value. All right. So when we say negative z of alpha by 2, it says find z of alpha by 2. We know alpha by 2 is 0.05. So that means we are looking for z of 0.05. We have to go to our table. Let's do that. Again, use the special table here. And it's z of 0.05 this time. All right, it's z of 0.05. So the z value, whose area to the right is 0.05, is 1.645. So we have to take that value and put it here. Just a second. So z of 0.05 is 1.645, right? That's the z of 0.05. So let's find the confidence interval now. Again, have the formula in front of you one more time. So x bar plus minus z of let's write it as alpha by 2, and then times sigma over square root over n, correct? So x bar given to us was 35. That's the sample mean. So it's 35 plus minus z of alpha by 2 we just found from our table is 1.645, and then sigma given to us is 4. So let's write the 4, and divided by square root over n was 25. So I'm going to write square root over 25, right? So we'll end up with 35 plus minus 1.645 times 4 square root over 25 is a 5. So again, this is a multiplication. 1.645 times 4 divided by square root over 25. And when we do this calculation, you have to do the 1.645 times 4/5 first, and then add that number, that value, to add or subtract that value to the 35. So 1.645 times 4/5 is 0.8 gives us 1.316. All right, so now we first subtract, and then we add. So 35 minus 1.316 is going to be 33.68, and 35 plus 1.316 is going to be 35.316. All right. So these are the endpoints of our confidence interval. And then finally, we have to write the interpretation in the expected form. So that we're going to write it as we are 95%, sorry, this is a 90% confidence interval, isn't it? Yeah, it's 90% confidence interval. So make sure you write that correctly. We are 90% confident that the population mean will be contained within the interval. Will be contained within the interval of 33.68 to 35.316, right? Now, before moving on to the next problem, I just want to make a correction to a calculation error I have here. 35 plus 1.316 should be 36.316. So I apologize for that. It should be a 36.316, right? 35 plus 1 is 36, and same thing here. We need to correct that. It's 36.316. So it extends, the interval extends from 33.68 on the lower end to 36.316. Now, question number 4 is an application-based word problem, which we have to approach a little bit differently, in the sense that we have to first read the verbiage very carefully and then extract the values of the different variables we will need in order to find the confidence interval. All right. Now, what I did here was I wrote out the formulae that we may be using to solve this question, to find the confidence interval, right? If you have the formula in front of you, then it'll be easier for you to identify which variables we should be looking for. Now, we will be using one of these two equations, one of these two formulae, right? The first one, which is x bar plus minus z of alpha by 2 times sigma divided by square root over n, is going to be used if the population standard deviation is known to us. And the other one, where we use the t distribution with the sample standard deviation, is to be used if the population standard deviation is unknown. So let's see if the population standard deviation has been given to us or it hasn't been given to us. So we have the data set provided to us in millions. This problem is about venture capital investments. So let me read through this first, all right? So it says venture capital investments is the area of application for this problem. It says a random sample of 18 venture capital investments in the fiber optics business center yielded the following data in millions of dollars. So here we have the data. There should be 18 of them, 6 times 3, 18 data points in millions of dollars provided to us. The question says, determine a 95% confidence interval for the mean amount mu, which is the population mean, of all venture capital investments in the fiber optics business sector. Assume that the population standard deviation is 2.04 million and the sum of the data is 113.97 million. All right, now they have told us here in this, okay, a lot of the information will or can be found in the portion of the question where they are asking us to find a confidence interval. All right. So here they say, assume that the population standard deviation is 2.04 million. This means the population standard deviation is available to us. Sigma, it says population standard deviation is 2.04 million. That's sigma. So since sigma is known, we will be using the z interval procedure, where we use z in the z value in the formula as well as sigma. All right, so I'm going to cancel this one out. We are not using the t interval procedure for this question, and that we determine by reading the question. All right, so now let's go on to extracting the values of the variables we need here. So we need x bar. So let me write that down here. We need a value for x bar. Then we need a value for z of alpha by 2, which we will we will find when we go into the question, but I'm just extracting the values of the variables we need at this point. All right, then sigma is given to us as 2.04 million. So 2.04, and n is 18, right? N represents the sample size, which is the number of data points, number of observations that has been given to us. So in this case, n is 18. All right. We have to find x bar. X bar, they haven't provided us the sample mean right away. All right, we have to calculate the sample mean. How do we calculate the sample mean? The formula for the mean is sigma x over n, correct? You have to sum up all the different data values, and then you have to divide it by the number of values in the data set, which is 18. So you can either go about adding 5.6 plus 6.27 plus 5.96 all the way up to 6.66 and divide that by 18. But the question told us that the sum of the data is 113.97 million. All right. So let's use that information instead of spending time adding up all these values, since they've already given us the summation. So let's do that. Sigma x would be 113.97 divided by 18, and that would give us a value of 6.332. All right, 6.332. 6.332. Again, let me write this clearly. This is 6.332. All right. Okay, so now let's go on to the problem. We have to first state what the confidence interval we are using for this question. They told us to use the 95% confidence interval. So CI would be the percentage value, which is 95%. From there, we derive the confidence level, which is the decimal version of 95%. So that would be 0.95. And then alpha would be 1 minus 0.95, 1 minus CL. So that would be 0.05, CL being 0.95, which we just found. And alpha by 2 is 0.05 divided by 2 would be 0.025. All right. And I'm going to rewrite the formula for the confidence interval that we are going to use. It's going to be x bar plus minus. We are using the z interval procedure because the population standard deviation is known. So this is times sigma divided by square root over n. That's the formula for the margin of error, this portion of the formula. Okay, so we have found, and I'm going to rewrite my values once more over here in this area. So it's easier for me to plug them in. X bar we found was 6.332, 6.332. And then we have sigma, which is 2.04, right? 2.04. And then we have now n is 18. And we know alpha by 2 is 0.025, but it's not enough to just know alpha by 2. We have to find z of alpha by 2. All right, z of alpha by 2 or z of 0.025. For that, we go to our table. So let me open up the table. So this is the special truncated z table for the special alpha values, and that you can find that below table 4. All right, for those who are taking statistics 2, this is the table you're going to use. Those who are taking statistics 1, it's a different table, and I will tell you where to find it from that table in a separate video. All right. So we are looking for z of 0.025, which is 1.960. All right. It's 1.960. This is the value we are using. Again, let me see if I can get the pen open. This is the value we are looking for, 1.960. So let's go back to just a second. Let me go back to the worksheet. Okay. So z of 0.025 was 1.960, right? So we have all the values we need. X bar, I'm going to write as 6.332 plus minus z of alpha by 2 is 1.960. Make sure you're writing 1.960 for z of alpha by 2 and not just 0.025. All right, please note that the formula has z of alpha by 2 and not just alpha by 2. If you're using 0.025, then you will get a completely wrong answer. You're not plugging in the right value. This is a very common mistake, and that's why I wanted to mention that. All right, do not make that mistake. It has to be z of alpha by 2. You have to take the step of, perform the step of referring back to the table with your alpha by 2 value and find the corresponding z value. All right. So 1.960 times 2.04 divided by square root over 18. All right. Now, before I go any further, it's very important for us to draw the diagram, sketch a diagram showing all your alpha values and your confidence level values in a diagram. All right, so let me do that on the side here. I will have my normal curve. Okay, this is my normal curve. At the center, I will have my X bar, and then I'm building my confidence interval around the X bar value. Our X bar value we found was 6.332. We have to find the endpoints of the confidence interval we are building around the center point. I'm going to extend the endpoints and have the vertical lines touch the curve, And now I'm going to shade the area bounded by the two endpoints, and that would be 0.95. That's the confidence level. So 0.95 is really the area bounded by the endpoints of the confidence interval. And then we have this outside unbounded area, which should be equal. All right, so this side would be 0.025, and so is the other side, 0.025. Together, the two unbounded areas would be alpha equals 0.05. All right, alpha represents the total unbounded area, the area outside the interval, and when we divide it into two, they represent the area on each side of our figure, of our diagram. Okay, so let's go back to the problem now. It's 6.332 plus minus 1.960. Now 2.04 divided by square root over 18 gives us a value of 0.481. All right, so we have 6.332 plus minus 1.96 times 0.481 gives us 0.942. And we have an interval of 6.332 minus 0.942 is the lower end of this interval, which will be 5.389. And the upper end would be adding, when you do 6.332 plus 0.942, that would be the value at the upper end, which is 7.27. All right. So here we are. We have negative z of alpha by 2 and positive z of alpha by 2 initially. All right. Which was 1.96, negative 1.96. And positive 1.96, and using this formula we just found the actual values of these end points, which was 5.389 and 7.27 at the upper end, 7.27. So our interval spans a range of values from 5.389 to 7.27. So we have found our interval. What we need to do is now interpret it in context of the problem. All right, so the way we will go about it is you have to first qualify your confidence interval and write it as we can be 95% confident. We can be, that's the interval we found, we can be 95% confident that the population mean, the population mean. Now, I would recommend the verbiage to use, you can obtain right from the question. All right, you take the verbiage from the question and write it, instead of trying to think how I should phrase it. Just use the verbiage in the question. So the population mean, just copy everything from here of all venture capital investments in the fiber optics business sector. So I'm going to write that the population mean of just a second, of all venture capital investments in the fiber optics business, in the fiber optics business will be contained in the interval, will be contained in the interval. Just state your interval 5.389 million. Okay, $5.389 million to $7.27 million. All right, so the key words or the key phrases here should be 95% confident. We are 95% confident. Or you can write at the 95% confidence interval. That's fine too. You have to say population mean, or you have to say all venture capital. All venture capital, when you use the word all, that implies population mean. All right. All venture capital investments in the fiber optics business will be contained in the interval. You have to state your interval correctly. Okay, so that is how we go about answering the word problems, application-based word problems. All right. Now, question number 5 is a question to check your understanding of the relationship between the confidence level, the margin of error, and precision. All right, so it says here, explain the effect on the margin of error and hence the effect on the precision of estimating a population mean by a sample mean when increasing the confidence level while keeping the same sample size. So keeping the sample size the same and increasing the confidence level, what effect it would have on the margin of error and the precision of the estimation. So think about it. Let me just sketch here an interval because it will be easier to understand. So let's say we have here on this scale X bar at the center, all right, and then we build a confidence interval around the X bar, and let's say this is a 95% confidence interval, all right, and the distance from X bar to each end of the interval is our margin of error E, correct? This is what the margin of error is. So this is the 95% confidence interval, let's say. Now, if we increase this interval to a 99% confidence interval, then it's going to become a wider interval, right? It's going to become a wider interval. So let's say the red here is 99%. So we've increased the confidence level, and what happens is the E, the error now, the margin of error has increased. When we increase the confidence level, the distance from the mean, from the center point to the ends of the interval, of the 99% interval, to this red bracket here, is more than what it was when we have had the 95% confidence interval, right? So what do you see here? When we increase the confidence level, the margin of error increased, all right? So let me write that for the answer. Increasing the margin of error, increasing the confidence level, not the margin of error. Increasing the confidence level increases the margin of error. But what does it do to the precision? All right. You see over here, going back to this sketch, to this diagram, when we were using a 95% confidence interval, we had to be more precise. Our estimate had to be closer to what the actual mean is, right? We had to guess, or we had to estimate within a narrow interval. With the 99% confidence level, we have a wider margin to make an error. So that means we can be less precise and still be considered within our interval, correct? So increasing the confidence level increases the margin of error but decreases the precision. So when we used a 99% confidence interval, we had a wider margin of error, all right? But it decreased our precision. We didn't have to be so precise. We can be off from the actual, the exact value by a wider margin. All right, that's what it means. Now, the second part of the question says, increasing the sample size while keeping the same confidence level. So if we increase the sample size while keeping the same confidence level, what impact would it have on the margin of error and the precision of our estimation? Now, when we increase the sample size, think about this, the sample size is n. So when we work with a larger sample size but use the same confidence level, what's going to happen is it's going to decrease the margin of error. Now I'm going to show you mathematically how the margin of error will get decreased when we increase the sample size. But let me just say this, when we increase the sample size, keeping the same confidence level, the margin of error will decrease and the precision will increase. So let me write that down and then I'm going to show you mathematically how that's going to happen. So increasing the sample size n, while keeping the same confidence level, will decrease the margin of error, E, and it will increase the precision. So when the margin of error decreases, when we have a narrower margin of error, it will increase the precision, right? You have to be more precise to the actual value. Now, mathematically, all right, what happens mathematically, let me just show you. The formula, okay, what is the formula for E? The formula for E is Z of alpha by 2 multiplied by sigma over square root over n, correct? This is the formula for the margin of error, which we add and subtract to the sample mean. Now, think about it. What happens when we increase the value of the denominator? Here, n is the sample size, correct? So when in any fraction, when we increase the value of the denominator, the quotient, all right, the quotient becomes smaller, correct? So let me work this on the side. Let's say we have 1/2, right? This is a fraction. 2 is in the denominator, all right? So this is 1/2. Now, if I increase the 1/2 to 1/4, 1/4 is a smaller value than 1/2, right? 1/2 is 0.5, 1/4 is 0.25. Now, if we increase it further and if we increase the denominator to 1/8, then that is an even smaller value than 0.25. If we keep on increasing it to 1/10 and 1/20, if we keep on increasing it, what is going to happen? The quotient is going to get smaller and smaller. So as we increase the denominator, n in this case, to a higher value, then this quotient is going to become smaller, which is going to make the the margin of error, smaller as well. All right, so that's how the margin of error gets smaller when we increase the sample size, because the sample size is being used in the denominator of this equation. So we are multiplying the z of alpha by 2 value with a smaller quotient when we increase n. So therefore the margin of error is also going to decrease. So that's how, as we increase the sample size n, the margin of error decreases, and when we have a smaller margin of error, we have to be more precise in our estimation. So that's how the precision increases, right? Now here's one more word problem on body fat. It's an application-based problem. So let's go through it. It says a sample of 27 female graduate physical therapy students had a mean of 22.46% body fat. Assuming that percent body fat is normally distributed with standard deviation 4.10% body fat, determine a 95% confidence interval for the mean percent body fat of all female graduate physical therapy students. All right. So let's again extract the important information, the data points we need in order to create the confidence interval. So the formula again is, it's best, like I said, it's best to start with writing out the confidence interval formula. So it's x bar plus minus z of alpha by 2 times sigma divided by square root over n. Now, if it were a t interval procedure, provided the population standard deviation is not known, then the z would become a t and the sigma would become a s. All right, so let's see what this problem involves. All right, so we have our formula. We need to know the value of x bar. We need to know the value of alpha by 2 in order to find the z value. We need to know sigma. We need to know n. All right, so let's list the values here. Do we know x bar? All right, so it says here a sample of 27 female graduates physical therapy students had a mean of 22.46% body fat. So that's the sample mean. It's the sample mean based on the measures of 27 female graduate physical therapy students. All right, so I'm going to write here for x bar, it's 22.46%. all right, then we need to know sigma. So is sigma given to us? Now it doesn't say anything about the standard deviation for the 27 female graduate students, right? All they tell us is the mean of the 27 female graduate students is 22.46%. It doesn't say anything about their body fat. I mean the standard deviation rather. Now over here it says assuming that percent body fat is normally distributed with standard deviation 4.10%. So this standard deviation that they've given us is the population standard deviation. All right, it does not apply to the 27 students in our sample, but this is the population standard deviation, 4.1, and that's why we have sigma here instead of S. All right, this value given to us is outside of this sample. This is the population standard deviation, so sigma is 4.10%. What else do we need? We need N, which is 27, right? So I'm going to write 27, and now we need the alpha by 2 value with which we can find our Z value. So the confidence interval, let's fill these values in. The confidence interval is 95%. The confidence level is the decimal version of 95%, so 0.95. The alpha is 1 minus CL, therefore 0.05. So by this time, you should be able to know how to calculate the alpha from the confidence level. And then we have to divide alpha equally into 2 parts, and that's going to be 0.025. And then I'm going to draw a picture here. All right, so here we have our diagram of the normal curve, okay, with X bar at the center, and we have the sample mean is 22.46%. All right, and now we will have to come up with our interval with our 95% interval, confidence interval. But in the diagram, I'm going to just extend the end points of the interval. All right, I'm going to extend the end points of our interval on both sides, and unfortunately I'm not able to draw a symmetrical figure, so let me try again. Let's say it's here. This is probably slightly better. All right, so it's still not symmetrical, but oh well. But the area bounded by the endpoints of our interval is 0.95. The unbounded area on either side of the curve is, together, it's alpha, which is 0.05, this value here, but each end has an area of 0.025, all right, 0.025, that's alpha by 2. So we have to find the Z values corresponding to each end of the interval. All right, so on the left-hand side, it will be negative Z of 0.025. On the right-hand side, it will be positive Z of 0.025. Okay, now if we look at the table, the Z table, we will now find that Z of alpha by 2. All right, Z of alpha by 2, which in this case is Z of 0.025, is 1.96. All right. Now I've shown how to look it up on the table in some of the previous problems. So this time I'm not pulling up the table, but if you're not able to find that, just look up the previous problems. All right, the solutions of the previous problems. But Z of 0.025 has a value of 1.96. So now we can just plug in the values into our confidence interval formula, which is X bar plus minus, and I'll write this down again, Z of alpha by 2 times sigma divided by square root over n. X bar is 22.46. 22.46 plus minus z of alpha by 2 is 1.96. Now plug in the value for sigma, which is 4.10. Again, this is multiplication. 4.10 divided by square root over 27. All right. And when we do the calculation for the margin of error, then 1.96 times 4.10 divided by square root over 27 evaluates to 1.546. All right. So that's our margin of error, 1.546. Now, when you subtract and add 1.546 to 22.546, we will get values of 20.91 and 24.01. So these are the end points of our interval. So here, this end is 20.91 and the right hand end of the interval is 24.01. Okay, so this is our interval. We can either write it as 20.91 and 24.901, but I think it's better to write 2 because it means that they are not, they are the end points of an interval. So all the values in between are also values belonging to that interval. Okay, so it's better to use the word 2. Now we have to interpret the answer that we found in context of the problem. Okay, you always have to begin with we can be 95% confident. So you have to qualify your interval. So we can be 95% confident that the mean body fat, all right, and then you can just pick up your wording from the question itself, that where it says determine a 95% confidence interval for the mean percent body fat of all female graduate physical therapy students. Just pick up the wording from there. We can be, I guess I lost the writing here. We can be 95% confident that the mean body fat of all female physiotherapy students will be contained in the interval 20.91% to 24.01%. Again, these are the key phrases you need to include in your interpretation. You have to write the 95% confident interval that you found, because if you use a different confidence interval, then it would be a totally different interval end points here. All right, so that's why you have to qualify your confident interval with a percentage value. So we can be 95% confident that the mean body fat of all right, if you're not using the word population mean, then you have to use the word all. So the mean body fat of all female physiotherapy students will be contained in this interval, and then you have to state the endpoints of your interval. All right, so you can pretty much use the same wording as in this question, that the mean body fat. It says mean percent body fat of all female graduate physical therapy students, and that's what I used in my interpretation here as well. Now, part B of this question says obtain the margin of error E for the confidence interval you found in part A. Now, we already actually found the margin of error when we did this calculation of Z of alpha by 2 times sigma over square root over n. That's the formula for E, but I'm going to just write it again out here now. If you've done the work and shown the work clearly for the previous problem, all you can do is for this part of the question, you can just write the value of E that you found above. All right, but using the formula, I'll just write it down anyway. So it's E equals Z of alpha by 2 times sigma divided by square root over n is the formula for E, correct? So let's plug in the value. Z of alpha by 2 we found was 1.96 from the table. That came from the table. Z of alpha by 2 is Z of 0.025 for this question, correct? And sigma, all right, sigma is 4.10 divided by square root over n should be square root over 27, and that should evaluate to 1.546. So you can just say E equals, you can round it up to the second decimal place here and write it as 1.55%. All right, now this answer should match whatever you found for the margin of error when you did this calculation above. Now this part C says explain the meaning of E in this context in terms of the accuracy of the estimate. Now the way you write this answer is we are 95% confident that our error in estimating the population mean mu by the sample mean is at most 1.55%. That's the maximum error we are allowed to make, all right, in order or while we are estimating the population mean from our sample mean. Now part D of question number 6, which was finding the confidence level of body fat percentages, says determine the sample size required to have a margin of error of 1.55% body fat with a 99% confidence interval. So here the exercise is about finding the sample size, all right? So they're asking us to find n. Now they want us to keep the same margin of error which we found before and which we used in finding the confidence interval. So the margin of error, which is E, stays the same. However, you'll note that they have increased the confidence interval. The confidence interval is now 99%. Earlier, we used a 95% confidence interval. So we have to find n based on these parameters. Now, there's a formula in your formula sheet. You can look that up in your respective formula sheets. There's a formula just to find the sample size. And that formula is actually derived from the formula to find E. All right. It is, you can come up with the formula for n by solving for n in this equation for margin of error. And when we did that, we came up with this formula for n. N equals z of alpha by 2, z of alpha by 2, times sigma divided by e whole squared. All right. So that's the formula to find the sample size. So what are the values we need in order to plug into this equation? We'll of course need z. All right. Z of alpha by 2. We'll have to figure out what alpha by 2 is. And then we'll need sigma. All right. We will need sigma, which is the population standard deviation, and which will stay the same as what we used for the body fat problem. And E has been given to us as 1.55%. So that's 1.55%. Now the value of sigma that we had used previously was 4.10%, right? That was the value of sigma given to us. So we have to find z of alpha by 2. Now you cannot use the same z of alpha by 2 that you used for over here, 1.96, or which you used in finding the confidence interval. Why? Because we are using a different confidence interval. We are no longer using the 95%. We are using the... Now, part D of question number 6 is asking us to determine the sample size required to have a margin of error of 1.55% body fat with a 99% confidence interval. All right, so this time we are being asked to find n, which is the sample size, using the same margin of error that we used previously. 1.55% was the margin of error we found when we came up with the confidence interval of the body fat percentage question, right? So this is a part of the same question. So we will keep the same margin of error, and that's what we are being asked to keep, 1.55%. However, we are given a different confidence interval. Previously, we used a 95% confidence interval. This time, we are being asked to use the 99% confidence interval. Now, there is a formula to find the sample size, and that particular formula is actually derived from the formula of the margin of error, E equals Z of alpha by 2 times sigma over square root over n. If we solve for n in this equation, we will come up with this formula here. It's Z of alpha by 2 times sigma divided by E whole squared. All right. So this is the formula for n, and this is also available in your respective formula sheets. You can look that up under the formula for this particular chapter on confidence intervals. So let's see what values we need to plug in into these different variables to come up with a solution for n. First of all, we need to know what alpha by 2 is. Correct? It's going to be a different alpha by 2 because we are using a different confidence interval this time. Okay? So once we find alpha by 2, we will need to find the corresponding z of alpha by 2. And then we will need to find sigma, right? We'll need to find sigma, which was given to us as 4.10%. And E, they've asked us to use the 1.55%. So we will write that down here, 1.55%. So let's figure out what alpha by 2 is, and therefore what Z of alpha by 2 is. Now, when we are using a 99% confidence level, then CL. All right, read this as confidence interval. Remember, we said that we use the percentage format when we talk about the interval. For the confidence level, it's 0.99, correct? So 99% converted to decimal. So if CL is 0.99, then alpha is 1 minus 0.99, which is 0.01. And therefore, alpha by 2 will be 0.01 divided by 2. So it's going to be 0.005. All right. Don't make the mistake. 0.01 divided by 2 is 0.005 and not 0.05. All right. So be careful about that. Don't miss out on one extra zero here. So we have to find Z of 0.005. So let me make this a little bit closer. So Z of 0.005, and if you look up your table, the Z table and the special Z table, you will come up with a value of 2.576. Okay, 2.576 is Z of 0.005. And now that we have all our values, let's plug it into this equation here. So N equals Z of alpha by 2 is 2.576 times 4.10 for sigma. So 4.10 divided by E is 1.55, and the whole expression is squared. All right. So when we do this calculation, you'll have to use your calculators. We'll end up with 10.562 for the numerator, 2.576 times 4.10 divided by 1.55, and this whole fraction has to be squared. Okay, and then we will come up with N equals. So this fraction amounts to 6.814, and then of course don't forget to square, and when we do that we'll come up with approximately 46.43. Now because sample size has to be an integer value, we cannot have a fraction in a sample size. Just round it up to the nearest integer. So let's use 47. So the answer for this is 47.